Hello, today's lesson is going to be on graphing linear functions. But before we can graph linear functions, we have to make sure that we know what a linear function is and what it looks like. So we have the conceptual idea, we have what the equation looks like, and we also have what the graph looks like. We can start off simply with a graph of a linear function. Looks like a line. Should be really, really simple. The rest of it can seem simple. We just have to make sure that we understand all the nature of it so that we can use it properly. So, when I studied 50 miles an hour as a rate of change, we recognize that miles per hour is the label. If you multiply 50 miles per hour by 10 hours, you get 500 miles. We can see the rate is miles per hour. My variable is the time that I can drive in hours, and in the end, we get a distance in miles. Distance equals rate times time. Generalizing, if we let x be the variable amount of hours, we can create an equation, d of x, distance of x, is 50 miles per hour times x number of miles or hours, and that'll give me a d in miles. So the three different components that we have here: the rate, 50 miles per hour, the slope of the line, 50, and the equation, 50 times x, all components of a linear function. And if a plant grows at 2 centimeters per week, the rate is 2 centimeters per week. The slope of the line is 2, and the equation is 2 times x number of weeks. So we have 2 centimeters per week times x weeks. That gives us a centimeter function. If we have 3/8 of a dollar per foot, or $3 for every 8 feet of rope, then we can actually recognize 3/8 of a dollar per foot is the rate. The slope of the line is 3/8, and the function is f of x equals 3/8 x, keeping in mind that x is the feet of rope. This is dollars per foot, and that converts everything into dollars for the function. Now we're working with a plant that has already got some height to it. So here it is. It's got a height of 2 centimeters. And what we learned from this problem is that the height increases at a 1/2 centimeter per week. So the rate of change is a 1/2 centimeter per week. The slope of the line is 1/2, same as the rate. And the equation turns out to be not just the rate, centimeters per week, times x, weeks. That gives us centimeters added to the original 2 centimeters for a total of centimeters in the function. And a test tube. Cubic centimeters this time. There were 3 cubic centimeters in the test tube at the beginning. Every minute there was an extra 0.4 cubic centimeters added. So the rate of change is 0.4 cubic centimeters per minute. The slope of this line is 0.4, which is the same as a 2/5 ratio, so 2 over 5. And the equation is 0.4 cubic centimeters per minute times the number of minutes added to the 3 cubic centimeters gives us a total cubic centimeter function over here. So each of these functions had something in common in their equation. When we looked in class, we found out that of these functions, and just give me a moment. These functions, among these functions, the ones that are linear are the ones that can be expressed by using some place to start and a rate of change or a slope to change. So these functions are not linear because they can't be expressed in the same way as these functions. So here there's a variable x in the denominator. Here there's a squared variable and an unsquared variable. Here there's a variable x in the denominator. I know I said this is an exponent, not a denominator. Here we have a square root, which seems to change things. And here we have a 1/3 power. Can you do that? Apparently. Anyway, none of these is going to be a linear function, but these all will be, because each of them can be expressed as start somewhere and then change at a specific constant rate. So this one, for example, could say I have $5 and I lose $1 every 3 days, and I can calculate my total money by figuring the number of days and then multiply by the rate and subtract it from 5. Here I can see that I start with $7 debt, and I'm paying off my debt at $2 every day, so I can figure out my debt by knowing the number of days. That'll tell me how many dollars I owe. This one looks a little different, but we learned that we can distribute the 2, and so this would be 2x when we divide by 2, and this would be 3.5 negative, which would be a starting value. So it doesn't matter where the x is. A linear function has a rate, and it also has a place to start. If you go back and look at all the functions that we looked at with the miles per hour and the rope and the centimeters of a plant and all of that, they all had the same general makeup. So we generalize by saying all linear functions can be expressed in the form of a plus bx or ax plus b. A and b could be any constant number, and then the variables will be x and f of x or y. So if I think about linear functions in either one of these ways, all I have to do is understand that the value of my function starts at one number and will change at a rate of b for every x. It's easier to talk about in context. Take this function right here, g of x equals 21 plus 0.5x. As an equation, it's meaningless, but if I put it in context, I could talk about a bus fare. The monthly cost to ride the bus starts at $21 to get a bus pass, but you pay 50 cents for every ride. So the amount of money you pay for the bus depends on how many times you ride the bus, and it's a linear function because it's a constant 50 cents for every ride. Here's a function. It doesn't have any context at all. Y equals 10 minus 2x. But I could express it as the money in my account starts at $10 and drops by $2 for every day. So now all of a sudden I see again constant rate of change. Here's the slope of the line that I'm going to be dealing with. Here's where I start drawing my line, and this represents your independent and dependent variables as always. So if you're going to graph a line, we can actually start by looking at the equation and trying to imagine what the line's going to look like. We could also put it in context, as you can see in green here. So here I start at $10. So when x is 0, we have $10. Every day, we lose $2. So a day later, I'm at $8. Now you can just take a ruler and draw the line between those 2 points, and every one of the points in this line will be a solution to that equation. To verify this, you just pick a value for x, like 4. Y equals 10 minus 8, or 2. When x is 4 days, we will only have $2 left, so we go over 4 days, we go up to $2. And sure enough, not only is it a solution to the equation, it is a point on the line. So this is what you need to do anytime you are asked to graph a line. You just need to first look at the equation, and using the slope, which is a rate of change, and the y-intercept, which is a place to start, you make up a context. So in this case, I'm just going to be really generic here and say we have 4 2/3 unicorns, and every day we lose a quarter of a unicorn. So then, as far as the context is concerned, I imagine I have some unicorns, even though there's a partial unicorn here, and we lose a quarter of a unicorn. Since that's weird, we could also say we lose a whole unicorn for every 4 days. We lose 2 unicorns over 8 days. We would lose 20 unicorns over 40 days. No. 80 days, something like that. Yeah, that's what it is, 80 days. So you get the idea. This rate of change is constant. It can be expressed in multiple ways. Then, after we've restated the context, identified the slope and the y-intercept, we make a quick sketch. So you just kind of visualize what the line's going to look like. I picture a line that's going to go down like this with a very flat slope because the slope is only a negative a quarter. Identify 2 points, the y-intercept and one other point, and after you draw the line, find a third solution to verify that your graph is accurate and correct. In other words, given this equation, y equals 4 2/3 minus a quarter x, I imagine the graph's going to look like this. I imagined it because I knew that I could put it in context. Here I said $4.66 and an account, and I spend 25 cents a day, or $1 every 4 days. To make the graph, I need 2 points. So I start with 0 4/5. And by the way, I should label this graph. No, I don't. I should. Never mind. This is a place to start, 0 4 2/3. And I said 8 days later, I'm going to lose $2 every 8 days. So I go from 4 2/3 to 2 2/3, and then I draw a point and the line. Finally, I pick another value for x, like 4, sub that into the equation, and get y equals 3 2/3. And I go over 4, up 3 2/3, and sure enough, that again is a solution to my equation and a point on the line. So that's what you need to do for these. I'm going to make an assignment. This assignment will be due to be posted. And I'll pick out a couple of these linear functions to have you graph using this full technique, step by step. It seems like busy work at first, but in the end, you're going to make some major connections and become really solid line graphers.